Good evening, everyone. Welcoming you all to the 33rd session. Sorry, there were some technical glitches, so we are not giving much intro today. We will talk about those other things tomorrow. So today we have two sessions. First one will be by on quantum mechanics in computer-aided drug design by Sudarshan and workflows for drug design by Vinod. So the first session will be taken care by Sudarshan. So over to you, Sudarshan, without much delay.
Thank you, Giri. Good evening, everyone. Sorry for the glitch once again. Yeah, so my name is Sudarshan Pandian. I'm working as a senior scientist in Schrodinger. So I'm a material scientist by training, and today I'm going to speak about how quantum mechanics can be used in the context of computational drug discovery.
Can you hear me?
Yeah, I can hear you.
Can you share your slide, please?
Isn't it not shared?
I can't see it. Is it?
Oh, really? Okay. Well, I'm resharing it again. Okay. Anyway, yeah. Do you see it now?
Yes, it's coming up. Yes.
Yeah. So sorry for that also again. Yeah, so my name is Sudarshan Pandian. I'm a senior scientist in Schrodinger. So today I'm going to speak about how quantum mechanics can be used in the context of computational drug discovery. So quantum mechanics can be used in multiple industries in multiple different ways. So today it's about how we can use it in the drug discovery. So you might have seen this slide numerous times already in Schrodinger's other presentations. Schrodinger has 5 different verticals, small molecule drug discovery suite. So that's what is being used for designing new drug molecules or new ligand molecules that are having potential of becoming a drug or a new chemical entity that's having some kind of bioactivity. And then biologic suite, where people try to design antibody, antigen, or protein, try to understand protein-protein interactions. Then we have informatics and machine learning tools. These are tools which are used for building QSPR, QSAR models, and also machine learning models for predicting properties of the material. Then for the visualization, we use PyMol. PyMol is kind of one of the very well-known software across multiple domains. And with the beautiful images which you see of the molecular level images which you see in many of these journals, most of the time they come from PyMol. And out of all these, we have a new tool called Materials for last 7 years now. So this material suite, which has quite a few number of tools, so where we can do simulations from quantum mechanical level to the coarse grain level. So anything that starts with a small molecule to a lipid bilayer, and also we can deal up to timescales of few femtoseconds to all the way up to microseconds or even up to milliseconds. So that's the time scale and then the length scale which you are speaking about. Today's context anyway is about quantum mechanics. In quantum mechanics, what we try to do is we try to deal with each and every electron in the system. Why? Because each and every electron plays a crucial role in predicting the defining the properties of the material or the ligand under the observation. So what we need to do is we need to understand what are the properties that are coming about the electronic structure of the quantum the electrons associated in the electrons that are located in the different atoms of the ligand molecule. So basically this the molecule might be a neutral molecule, but there are partial charges on each and every atom because of the electronegativity differences between the different bonds they create between different types of atoms. So basically, if there is an oxygen connected to the hydrogen, so the hydrogen is going to be highly positive and oxygen is going to be obviously negative. So though the molecule is going to be neutral, even if you take a H2O molecule, the two hydrogens are going to be having some kind of partial charge and the oxygen is going to have some kind of partial charge, which leads them to basically the hydrogen bonding interactions when they come together, when they sit next to each other. So when we look at the binding pocket environment where you have a protein molecule and the incoming ligand molecule is sitting in the binding pocket and having only the non-bonded interactions with the protein molecule, there is no chemical bond created between the ligand molecule and the protein molecule. In that cases, it's only the non-bonded interactions that drive the interaction between ligand and the protein molecule. So these non-bonded interactions which gives us the binding energy between the ligand and the protein. So if our partial charges are wrong, that means our interaction energies calculations are going to be wrong. First thing. The second thing, so these quantum mechanical calculations also allow us to calculate the bond lengths, bond angles, dihedral angles, and what is the strength of these dihedral angles, what is the kind of energy we require to rotate a bond or angle around particular bond under the consideration. So this would allow us to explore the conformational space of the given ligand molecule. So whether the ligand molecule go into this binding pocket, given binding pocket of a size of a smaller size or a bigger size. So that has to be understood from this torsional angle bending and torsional angle rotations. So if our energies are wrong, everything else is going to be wrong. For that matter, we have to spend really good amount of time in quantum mechanical calculations. But if you look at historically, over the last 50 years, there are plenty of versions of force fields are developed for protein molecules, because the protein molecules are usually made up of 20 amino acids. So for the 20 amino acids, people have been developing force fields since 1970s. So over the 50 years, we have revalidated multiple times to get the force fields correctly fixated for the protein structures. So if you take many force fields that are available in the public domain, so many of them can predict the protein properties accurately. But when it comes to ligand-protein interactions, the ligand molecules are of completely new chemistry. When the ligand molecules are having something unique, like a metal atom or a completely new chemistry, so those molecules, the same force field can be applied that is been developed for the protein structures. So there we have to use quantum mechanical calculation to revalidate the force field parameters. So that's the first thing which is kind of required when we are trying to develop new molecules. But now we are speaking about the ligand scale of 10 to the power 60. There are a lot of new chemistries that are coming into picture. There are a lot of new molecules that are coming into picture. So for these molecules, there might be some torsional missing. There might be some new chemistry or new bondings which is not going to have right kind of force, partial charges. So for them, they have to fit these quantum mechanical calculations. So for the initial screening and all, we can use maybe the existing force fields. But once we are in the stage where we are picking the molecules, handpicking the molecule as a hit molecule or as a lead molecule, it is indeed suggested or advised to validate these parameters using quantum mechanical calculations. So that's a quantum mechanical calculation introduction, which I want to give in this slide. Of course, in Schrodinger, we can do quantum mechanical calculations. From there, we can take the parameter set and then we can use it in the molecular level simulations. That's where like you can do docking or molecular dynamic simulations. When we go to coarse grain level simulations, where we do like permeation, penetration, the transport studies of diffusion of drug molecule through a skin membrane or a cell membrane, that kind of things can be visualized. That kind of things can be simulated using coarse grain level simulations. So putting these things together is called Schrodinger's material science suite. Schrodinger material science suite is a unique toolkit where you have things for building models, any different type of model that you are known for any different type of material. So once we have the model of the material, we can do quantum mechanical engine or a molecular dynamics engine to do the simulations. So once we do the simulations, we can predict the properties. And to do that one, we have automated workflows, and as well as if you have existing data using which we can build a automated QSPR models or machine learning models. Then periodic DFT, which is again quantum mechanical level calculations for interfaces, especially when we speak about nanoparticle drug molecule interactions. Let's say like a gold nanoparticle can be used as a drug carrier molecule. So when you use gold nanoparticle as a drug carrier molecule, basically you don't need multiple excipients. You can do a lot of amount of loading of your drug molecule in smaller drug carrier molecule. So in those cases, if you want to understand the gold nanoparticle and drug molecules interaction, so that can be done using quantum espresso interface, where we can build a gold surface, put a drug molecule on top of it, and then see what kind of interactions are there when we have different types of terminations of surface. So that's at the periodic DFT level. So today, anyway, in the context of drug discovery, how we can use quantum mechanics, that's what we are going to speak about. Before we go in there, I want to give a brief history of how quantum mechanics came into picture, why quantum mechanics is important. So all the things which we speak in this vertical three, like or even in the computer-aided drug design, everything started because of this guy, Sir Isaac Newton, and in the 17th century, he came up with the three beautiful laws. Newtonian equations and Newtonian laws. So this guy, before 45 years old, before he turned into 45, he was able to come up with this unique theory, which still explains things that are happening at the molecular level to the motion of planetary motions around our our solar system. So he explained everything from solar system's movement to a small simple particle movement, using three simple equations. And this was all done during Corona kind of situation. So when there was a second wave of plague in UK. He was house quarantined for 6 months. During that time, he did this actual research and he came up with this idea of Newtonian equations. So we are in the same situation. We are working from home most of the time. So probably we might have, or some of us or one of us can come up with something unique like this to solve this pandemic situation, or something, a groundbreaking theory or groundbreaking approach to problem solving, this current for the current situation. So this is all started with this guy. For 200 years, everything was explained using Newtonian equations. Then came along a band of bandits. So these guys, so they started to discover what is there at the atomistic level. They started looking into the atom. They found the atom is 99.14 and a 4. So percent is empty. So only 0.14 zeros and a 6 is percentage filled with some mass. The rest of the part of the atom is completely empty. So what is that? Then they found in the core they have protons and neutrons. Electrons are going around it. So there are multiple experiments that are being carried out. And then when we go and apply Newtonian equations at that level, at the subatomic level, it failed. Okay, it completely failed. So there are different levels where it failed. So photoelectric effect is one of that level where it couldn't able to explain the Newtonian equation, couldn't able to explain how the photoelectric effect happens. And also again the quantas or the quantum. So that's the thing which has been a black body radiation. So that's the thing which has been explained by Max Planck in 1900. So there are failures of Newtonian equations. Then they came up with a new theory that's called quantum mechanical theory. So this quantum mechanical theory has two different eras. From 1900s to 1926, this is called world quantum mechanics theory, or just a quantum mechanical theory of the beginning of the quantum mechanical theory equations. So then in 1926, Schrodinger came along. Schrodinger, with his wave equation, he could able to explain things that are at the subatomic level. So he basically differentiated the function from the functional. Okay, so this is the conference which happened in 1927. That's the start of the new quantum mechanical era. So in this picture, there are 29 people, out of which 17 are Nobel laureates. And this guy right here, he's Schrodinger, and he is father of new quantum mechanical theory. So 1927, people came up with a theory that can be used to solve solve the quantum mechanical equations, or Schrodinger's equation for many body systems. So Schrodinger equation was can be solved thoroughly, completely by only a two-particle system, a hydrogen atom where you have a proton and electron. The moment we introduce a third particle, or it could be a subatomic particle, it is. So when we go to helium atom, so it cannot be solved completely. We have to make some kind of approximations. So Hartree-Fock method is one of the approximation where it can be used to solve the many body system. Then again, Thomas Fermi model, Born-Oppenheimer approximation. So these are the different approximations which were started in 1927, which is the start of new quantum theory era. So then 1930s, people came up with a lot of other ideas. A couple of them are worth mentioning: coupled cluster methods, MP theory. So these are the theories which are used to solve many body systems. So now they were all doing it in 1930s to 40 using paper and pen. You can't go with much of a detail in 1930s and 40s with paper and pen. So 1945, we have an invention of computer. Then 1964, this two gentlemen, Kornberg and Kohn, so they came up with a theorem where they can use they can solve the quantum mechanical theory for a bigger system, molecular system. So that led to density functional theory calculations being simplified and then doable in the computers. Then in 1970, first computational software came out, John Purple. So this particular gentleman, he got a Nobel Prize in 1998. And 1990, Jaguar, a quantum mechanical software engine, which has been released by Schrodinger in 1990. Now, if you look at it, there are 100+ quantum mechanical softwares that are available. So this is a brief history of quantum mechanics. So it all started with proving that Newtonian mechanics are not working at the subatomic level. Then we were able to solve it for simple hydrogen atom only. Then people came up with the approximation theories that can allow us to do it for molecular systems. Now we have 100+ quantum mechanical softwares available. So which one to pick? What are the things to choose? So that's kind of a big puzzle or a big mess unless we do a lot of reading. So quantum mechanics are taught at a university for one full year and 2 semesters. So we can't cover it in a 45 minutes lecture. So this is a brief history of it. Now in the practical applications, how this quantum mechanical theory can be used for understanding real life situation problems, as well as in the drug discovery context, how it can be used. That's what we are going to discuss. Okay. Before we go there, why do we need to care about quantum mechanics? So anything that is happening at the macroscopic level that can be traced back to subatomic level. So if water is boiling at 100 degrees Celsius, what is happening to water molecule at 100 degrees Celsius? As I said already, so hydrogens are positively charged, oxygen is negatively charged. Oxygen has the 2 lone pair electrons also. So when 2 water molecules come close to one another, the hydrogen is trying to interact with the lone pair electron and the oxygen. So that leads to hydrogen bonding creation. So when they are at the room temperature, when they are below room temperature, the number of hydrogen bonding each water molecule can create is 4. So for 2 hydrogens, it's 2. The 2 lone pair electrons on the oxygen can interact with the 2 hydrogen atoms from the neighboring water molecules. That means it can have 4 hydrogen bond interactions at a room temperature or at the normal conditions. When we heat it up, the intensity of the OH touching mode is going to increase because of the energy, the thermal energy which is coming in. So the intensity of OH touching mode is going to increase, because of which the number of vibration frequencies which are happening is going to increase enormously with the increase in temperature. Because of that, now the hydrogen is not going to see the neighboring oxygen molecules lone pair electron, because I'm going so fast, the intensity is so high, I'm not going to be able to see that lone pair electrons which are out there. Because of it, the hydrogen bonding interactions are going to be reduced, or hydrogen bonding interactions are not going to happen. Now these 2 molecules are getting kinetic energy also from the heat energy, so they try to go away from one another. At 100 degrees Celsius, basically there is no way they are going to see each other and form a hydrogen bond. That's why they evaporate, they go away from one another, they go into vapor state. So this is a simple molecular level explanation of why water is boiling at 100 degrees Celsius. The same way how a drug molecule is interacting at the binding pocket, how a drug molecule is basically preventing the conformational change of the protein structure. So everything can be traced back to the molecular level interaction or the subatomic level interaction. So for that matter, we have to really understand and spend time on subatomic level. So that's why quantum mechanics matters. Okay. Yeah, so as I told, in Schrodinger, we use Jaguar, which is probably the fastest DFT engine available. We can do Hartree-Fock level calculations, DFT level calculations, or MP2 level calculations using pseudo-spectral approach, which is kind of very robust, because of which we can do calculations at a very high speed. And also we can deal systems that are of very big size. So when we speak about systems of, like, let's say 200, 300 atoms, which other softwares might take some really lot of time to calculate, with Jaguar, you can do it within a day. Optimization under the property predictions. Yeah, structural optimizations, computational IR spectra predictions, computational NMR spectra, absorption spectra, emission spectra. So probably spectra predictions. And also if there's a chemical reaction there, we can calculate even the transition state searches. And also we can do we can use the transition metals. So for organometallic complexes. And also for the solvent effect, we have 2 different models for the implicit salvation models, PBF and PCM models. So we can see the impact of what is the impact of the solvent also for the given molecular system. So the HOMO-LUMO orbitals, which can be used as a tool for fitting your QSPR models. Again, more details in the later slides. Okay, so that's the Jaguar engine. So as I said, it's probably the fastest engine. You can see. So this kind of very complex molecules, which are very tough to optimize in any of the other softwares out there. But with the Jaguar, you can really think about optimizing these structures. So you can do a single point energy calculation in 1 hour. Let's say if we start from a really energy minimized structures from a right kind of force field, we can easily do like a 50 iterations in 2 days time. So that means we can really optimize this molecule, this kind of very big and very complex molecule also. So yeah, the time taken is 10 to the power 2.3, which is basically the number of atoms increases, that the time is going to increase, but it's not going to increase linearly. It's or exponentially. There is a scale up. So with the number of CPUs, we really can do quick calculations for bigger molecules also with the Jaguar. And what do we need to do this kind of Jaguar calculations? What do we need is a simple molecular structure. Once we have a molecular structure, we have to select few things like a basis set, which we want to use for treating this molecule, and the basis functional, which we want to use. Then once we do select these 2 things, it's about the calculation type. So do I want to calculate a single point energy? I'm getting the structure from a experimental crystal structure. So then I just want to calculate the energy of the crystal structure. So then you can do a single point energy calculation. Or if you want to do optimization, because we don't know what is the lowest energy conformation available for this molecule. So we want to do a optimization, then we can do optimization calculation. Torsional scan. For example, we want to see how much of energy we have to spend around to rotate this molecule around a particular bond. So then for that we have to do a torsional scan. So we can do a torsional scan kind of calculation. So we have to specify the calculation type. Then what are the properties we want to calculate? For example, as I said, we can calculate the spectra, we can calculate the ESP charges, the surfaces, the homo-LUMO orbitals, which eventually actually means the electron accepting character and the electron donating character, ionization potential and the electron acceptance properties. And also if we want to print out outputs, what kind of output level we want to print. So these are the information which we have to select before running any DFT or quantum mechanical level calculations. So but these numbers are the ones which usually give trouble to many of the beginners. So now we will break it down how we can choose the right kind of basis set and basis functional for any ligand type of molecules. Okay. Yeah, so when we speak about basis set is a atomic property. So for any given atom in the system, you can choose a separate basis set. So basically 631G double star, which is a basis set that represents each and every atom in the system. So if you want to change a different basis set for different atom, you can choose it. In many of the softwares, it is possible to choose atom-based basis sets. These basis sets basically represent the orbital around each and every nucleus. So how sophisticatedly we are defining the orbital space around each and every nucleus is defined by the basis set. So 631G is a basis set which is usually used for organic molecules, because the organic molecules tend to have only carbon, nitrogen, oxygen, fluorine, so some kind of halogens, as well as most of the time carbon, nitrogen, oxygen. So for them, 631G has very well defined s and p orbitals. Most of these components don't have d orbital. So 631G doesn't have d orbital, but it has a very good representation of s and p orbital. So for organic molecules, we can use 631G with some level of accuracy, and it tends to produce good amount of good type of results with the right kind of basis functional. Most of the time, when we worry about structural properties, people use B3LYP. If you look at articles, many of the time B3LYP 631G star is kind of used by default for any kind of organic molecules. The moment we bring in metallic systems or any metallic atoms or any atoms that are having d block d orbital, then we have to switch from 631G to something else. So in Schrodinger we have LACVP, Los Alamos laboratory-based basis sets, which we use for systems that are having d orbital, d orbitals, or atoms that are having d orbitals. And when it comes to basis functionals, when we are worried about the energy calculations, especially when you are doing transition state calculation and stuff like that, so where we use MO62X, so which tends to produce energy, predict the energies in a very good way compared to B3LYP. When we worry about the structure, we use B3LYP. When we worry about the energy, it's mostly MO62X. So these are the two parameter set which you have to choose. But this is the logic behind choosing this kind of parameter set. So once you choose this parameter set, the rest of the things depends upon what do we need. So do we need to optimize it? Do we need to calculate the charges, or do we need to do a single point energy calculation or the torsional scan? So based on the property of interest, we can choose the options and start the simulation. Okay, so as I said, why do we need to worry about it? So when we speak about small molecule drug discovery or structure-based drug discovery, we worry about ligand protein interaction. So the ligand is going to sit in the binding pocket, how it is sitting in the binding pocket, where it is sitting in the binding pocket, and what kind of interactions it's having with the protein. So these interactions are mostly dominated by these two non-bonded interactions. Either it's going to be dominated by the van der Waals type interaction or the Coulombic type interaction. In the Coulombic type interaction, you can see these two parameters Qi and Qj. So these two are the partial charges that are sitting on the ligand and the partial charges that are sitting on the atoms of the protein. If these two values are wrong, this particular component is going to be wrong. And also, if these values sigma and epsilon, these values are wrong, then the non-bonded interactions which we are calculating from the van der Waals type is also going to be wrong. So, but when we look at the protein ligand interactions at the binding pocket, this is dominated by hydrogen bond interactions, pi-pi interactions, pi-cation interactions, dipole-dipole interactions. So these interactions are strongly driven by these two types. So then we have to have the right kind of parameters. As I said, force field plays a crucial role in calculating the binding energies, and also the torsional angle conformations of the ligands. So what kind of conformational space which we have, that is defined by the torsional, the dihedral parameters. So this k theta value is wrong. That means the bendable angle is not given as a bendable angle. You are going to miss whole lot of phase space or the two conformations from the ligand. So that means maybe a molecule that can be properly put in there in the binding pocket is not going to be docked properly because of the wrong conformational search. So if you are using Schrodinger, if you are using glide, you don't need to really worry about it because Schrodinger has the best force field available, so that would take care of it. But if you are using any open source tools or any tools that are, you are not completely aware of what are the things that are being done at the background, then you have to absolutely make sure these things are right and these things are done in a proper way. If these things are not done in proper way, the binding energy calculations that we are doing at the molecular level has to be revalidated or has to be cross-examined with some other tool, or it has to be benchmarked, and then you have to go for the actual study. Okay, so what is the impact of the torsional scan? So that's what we are going to show in this slide. So if you look at this particular molecule, and if you look at carbon, nitrogen, carbon, carbon, these four atoms, and then look around this carbon nitrogen angle, a bond. So if there is a rotation that is happening around this particular axis, that means this benzene ring is going to rotate. So if this benzene ring is rotating, so this benzene ring can have a pi-pi interaction, or it's not going to have a pi-pi interaction depending upon this rotational energy. So you can look at it. So this is the one which is used in OPLS 2005. And then here you have black, which is coming from quantum mechanical calculation, and the blue is the one which is kind of currently being used in Schrodinger in OPLS 3 force field. So that means we are very close to the real life situation, even in any type of ligand environment, because of which we can really do accurate calculations in OPLS 3E force field. And these force field parameters are coming from quantum mechanical calculations. If you are not so sure about your force field parameters, obviously you have to run a quantum mechanical calculation, you have to fit the parameter and then redo the docking. Okay, so here is a force field builder which is available within the Schrodinger package for building force field parameters, whichever is missing. But in the case of Schrodinger, you won't find it often. But if you are using some other software, you please make sure that you have the right kind of force field parameters. Okay, so because in Schrodinger, we spent really huge amount of energy and money in developing this force field. Over the 3 years of time, about 75 scientists, they developed this OPLS 3E force field, which covers about 95% of chemical space. Now it's even higher than 95%. So because of which these force field parameters are going to be obviously there. But if there are some of them missing, we can on the fly fit it using the force field builder. Okay, using quantum mechanical calculation. Okay, so when we speak about the force field charges, you can see. So this is coming from force field A, this is coming from force field C. I don't want to name them, but here is the one which is coming from OPLS 3E, and here is the one which is coming from OPLS 2005, and the one from the DFT calculation. You can see. So for time being, let's pick up this fluorine atom. So this is a favipiravir molecule, which is kind of now used for treating coronavirus at the current situation. So you can see this fluorine atom, which is there in the force field A, which is giving 0.25. In the force field C, it is giving 0.25. In the OPLS 3E, it's using minus 0.191. So here in OPLS 2005, it's 0.112. In quantum mechanical DFT calculation, you can see it's 0.191. So though most of the spaces, the energy looks or the charges look similar, by the color you can say the charges look similar, but you can see the charges are significantly different in different atoms. Okay, so because this small difference in the charge, what kind of difference it's going to make? So when I docked this particular molecules in a binding pocket where favipiravir is supposed to interact, the binding energy difference in this case, which is already proven case, was already close to 1 kilocalorie. Okay, if I use these charges, the difference between them are these charges and these charges, the energy difference was 1 kilocalorie. So let's say you are setting up a cutoff to select a hit molecule as a, let's say 7 kilocalorie. What happens if your actual molecule is around 6.4 or 6.3? So you have to make sure these charges are right. So how do we make sure these charges are right? Run a simple quantum mechanical calculation. It won't take long, again with the Jaguar. So then you can compare the charges with whatever the charges that are coming from force field. Are they similar? Are they very close? If they are very far away from one another, basically you have to change the charges or you have to change your force field. Okay, so that's why quantum mechanical calculations are key in doing right kind of simulations and right kind of docking procedures. Okay, so here is another example which is published in Schrodinger's website. You can see it. So when you have metals which are there in the binding packet or close to binding packet vicinity, in the vicinity of the binding packet, we have to do QPLD, quantum polarized ligand docking, which is available again within the framework of Schrodinger, where we re-optimize the force field parameters of the ligand, charges on the ligand, so that we can predict the binding energy correctly. You can see, so compared to glide score, even the ones which are coming from the quantum polarized ligand docking are much more accurate, closer to the experimental values. The RMSD values are very, very close compared to experiments. So when you have metal atoms, especially close to the binding packet, you really have to do quantum polarized ligand docking. Okay, you can see. So compared to glide, QPLD is more accurate, and then also RMSD is very, very small compared to experiments. Okay. Yeah, when we speak about covalent inhibition, which is kind of the case for coronavirus situation, or also when people work on the cancer treatment and all, so people look at this kind of warheads which are used for doing the covalent binding between a ligand molecule and the protein molecule. So we have to predict what kind of bonding that can happen between the ligand molecule, covalent bonding between the ligand molecule and the protein structure. So we have to understand what kind of warheads can be used effectively, where this reaction can be driven or the bonding can be driven in a favorable way. So for that we have to find out what is the energy barrier or the reaction energy barriers. So we have again automated protocols to calculate the transition state searches. So we can calculate both kinetic energy barrier as well as the thermodynamic energy barriers. So the thermodynamic energy barrier will tell the difference between the energy difference between the reactant and the products, and the kinetic energy barrier which gives you what is the kind of hilltop it has to cross to go to the product side. So we can calculate both of them automatically. We have an auto TS engine to calculate the kinetic energy barriers. We have reaction workflow to calculate the thermodynamic energy barriers. So which would allow us to choose the right kind of warhead for covalent docking. And also here is the one which is predicted from the TS calculation, and this is the one which is predicted from the reaction calculation. So this is possible to avoid expensive transition state searches. We can use our reaction workflow to calculate which warhead is going to be very useful for us. So we are even working on an automated way to find right kind of warheads for given environment. If you are working on a covalent docking, which is the case in few of the problem statements in the DDH, so then we really have to worry about this reaction barriers, which can be calculated using quantum mechanical calculations. So when it comes to QSAR properties or QSAR models, so which is usually the case when we don't have the protein structure. When we don't have the protein structure, just based on the known activity, how do we establish that data, use the data to predict the property or design the new molecule? So for that, we use QSAR models. So we basically get the chemical structure. From the chemical structure with the known property, we are trying to understand what kind of unknown property or a known property can be fitted as a model for the unknown molecule, how we can predict the property. Okay, estimate the value of the property. So here it could be chemical property or intrinsic properties, but now over the last decade or so, people use these properties basically, which are electron affinity, ionization potential. These things come from quantum mechanical calculations. HOMO-LUMO energies. You can go and check. There are hundreds of publications out there which use HOMO-LUMO energies as descriptors for QSAR or QSPR models. Okay, and then multipole moments, dipole, quadrupole, octopole moments. As I told you, again, your binding energy is strongly influenced by the partial charges on each and every atom. So then, if you can use them as descriptors, if you can use them as a property to fit your QSPR model, that means you are going to get a right kind of QSPR model. So for that reason, people use this kind of quantum-based descriptors. Again, in Schrodinger, we have automated workflows to calculate these QM-based descriptors. Molecular descriptors for a whole lot of molecules, hundreds of molecules, can be calculated with a single click of a button. We'll get all these properties, which can be used to fit a QSPR model in an automated way. Okay, and also we have automated workflow to understand the ligand molecules. So if you have a ligand molecule, so let's say this ligand molecule is going to go through some kind of degradation or some kind of reaction, chemical reaction. We have to find out what is the weakest link in this molecule. So we can find out what is the weakest link in this molecule, where this molecule is going to break into pieces. So what kind of degradant product can come out of this, fragments that can come out of this particular molecule. And also, when you put this molecule under different pKa conditions, pH solutions, how this molecule is going to behave. Because when you are doing docking, you have to take the right kind of representation, tautomeric representation, as well as right kind of ionized state representation. So for that matter, we have to calculate the pKa. So we can do both site-wise pKa as well as the macro pKa of the given molecule. And also, what are the different ways this molecule can go through a reaction. When a heterophile is attacking, how this molecule is going to go through a reaction. When a nucleophile is attacking, how this molecule is going to go through a reaction. So that information can be also derived from a automated workflows. Again, Vinod will be giving you a more detailed workflows on drug discovery idea, but here is a workflow for, here are the workflows for how you can predict and understand your ligand molecule in an effective way. Once you have a hit molecule, you want to understand everything about your hit molecule. So then we can use these tools to understand everything about your hit molecule before you go into the next level. Okay, so to put in a summary, QM plays a crucial role in defining force field parameter, which eventually plays a crucial role in finding the binding energies. And again, the two different ways, torsional sampling as well as the partial charges, they play a huge role in finding right kind of binding poses as well as the binding energies. And when it comes to ligand-based drug discovery, people use this kind of QM-based descriptors to fit the model, which tend to produce much more effective models compared to traditional models. And also when we do covalent docking or covalent inhibitor build generations, designing, so you need to understand the reaction energy barriers for which you need to use quantum mechanical calculations. So these are the three different ways I would suggest quantum mechanics can be used in the context of drug discovery. So this is where I'm going to stop my presentation. I'd be glad to answer any of your questions. Thank you for your patience, and over to you, Giri.
Thank you so much, Sudarshan, and apologies to all the participants, including to the speaker, for the glitches we had during the initial phase. Now, one of the common question is that is Jaguar module will be available with the virtual tool room for the hackathon?
Well, it is going to be available within the Schrodinger suite, and we are offering Schrodinger suite for all the participants of DDH. Yeah, it should be available with for all the participants of Schrodinger. DDH. Okay.
And you also rightly mentioned black boxing is not the right way. You have to verify and check each and every step that gets validated. And also regarding the force field generation, also you mentioned and emphasized on including checking the ligands on Foucault functions, including the reactive side, degradation, bond degradation. These are all key points actually one has to consider when they think about PKPD studies and many more, I think.
Yeah.
Yeah. So due to the time short, we are restricting to these two queries. So shall we go ahead with the next session? And thank you so much, Sudarshan.
Yeah, thank you, Giri. Thank you everyone for listening. Yeah, let's hope in DDH you all get access to this quantum mechanical software and you use it effectively, effectively as well. Thank you. Thank you all.
Absolutely. Thank you.